Jupiter. A world so enormous it defies every intuition we have about what a planet is supposed to be. A place where winds howl at speeds that would strip a continent bare, where a single storm has outlasted entire human civilizations, and where the sheer gravitational muscle of one planet has quietly shaped the destiny of everything else in our solar system, including us. It is the undisputed king of the solar system, not by title, but by sheer physical dominance. And yet, for all the attention it receives, most people only scratch the surface of what makes Jupiter so extraordinary. Today, we are going deep on Jupiter, its structure, its history, its extraordinary influence, and what humanity's most advanced missions have revealed about a world we once thought we understood. Before anything else, you need to recalibrate your sense of scale. Jupiter is not just a big planet. It is a planet that makes the rest of the solar system look like a footnote. Its diameter stretches across approximately 143,000 kilometers at the equator. To put that into perspective, you could line up roughly 11 Earths side by side just to span its width. But width alone does not tell the whole story. In terms of volume, you could fit over 1,300 Earths inside Jupiter and still have room left over. And in terms of mass, Jupiter outweighs every other planet, moon, asteroid, and comet in the solar system combined, and then does so 2.5 times over. What makes this even more striking is the relationship between Jupiter and our own Sun. The Sun accounts for around 99.86% of all the mass in the solar system. Jupiter by itself accounts for the majority of what remains. In a very real sense, our solar system is the Sun, Jupiter, and then everything else. This mass imbalance has a fascinating physical consequence. When two objects orbit each other, they don't orbit around the center of the larger object. They orbit around the shared center of mass, called the barycenter. For most planet-Sun pairs, this barycenter sits deep inside the Sun. But Jupiter is so massive and so far from the Sun that the barycenter between the two actually sits just outside the Sun's surface. Jupiter doesn't orbit the Sun so much as the two of them perform a slow, stately dance around a point in space between them. It is a subtle thing, but it tells you everything about just how heavy this world truly is. Look at Jupiter through a telescope and what you see are bands, sweeping colored ribbons of cloud wrapped around the planet in alternating light and dark stripes. It is one of the most recognizable sights in the night sky. But that banded surface is just the outermost layer of something far stranger underneath. Jupiter does not have a surface in any meaningful sense. Below the cloud layer, the atmosphere simply gets thicker, denser, and hotter as you descend. There is no moment where gas becomes solid ground. The transition from atmosphere to interior is gradual and deeply alien. The outer atmosphere is composed primarily of hydrogen and helium, in proportions not unlike those of the Sun, roughly 90% hydrogen and about 10% helium, with trace amounts of methane, water vapor, and ammonia. It is these trace compounds, particularly ammonia and sulfur-based molecules, that give Jupiter's clouds their distinctive palette of browns, oranges, and creamy whites. As you descend deeper, the pressure climbs rapidly. Hydrogen, under these conditions, does not behave the way we are used to. It transitions from a gas to a liquid, and eventually, under extreme pressure, into a state called metallic hydrogen, a form of the element where electrons move freely through it like a conductor, giving it properties we associate more with metals than with gas. This metallic hydrogen layer is likely responsible for Jupiter's extraordinarily powerful magnetic field, one of the strongest of any planet in the solar system, extending millions of kilometers into space. At the very core, current models suggest there may be a dense, rocky, or icy center, though the conditions there are so extreme that our understanding of what matter even does at those pressures remains incomplete. Some models suggest the core could be partially dissolved or fuzzy, blending gradually into the metallic hydrogen around it, rather than forming a sharp boundary. No discussion of Jupiter is complete without its most famous feature, the Great Red Spot. This is a storm, a single continuous anticyclonic storm that has been observed, documented, and studied for over 3.5 centuries. When European astronomers first noted it in the 1600s, the Roman Empire had already been gone for over 1,000 years, and the storm was already spinning. It is vast, even in its current, somewhat diminished state. It is wider than the Earth. For most of recorded history, it was considerably larger. At certain points in the 19th century, it was estimated to be 4 times the width of our planet. It has been shrinking, a process that has accelerated in recent decades, and scientists are actively debating whether it will eventually dissipate entirely or stabilize at a smaller size. The color, despite centuries of observation, is still not fully explained. The leading hypothesis involves complex chemical reactions driven by ultraviolet radiation from the sun, breaking apart ammonia and acetylene compounds at high altitudes and producing red-tinted molecules in the process. The storm sits higher in the atmosphere than the surrounding clouds, meaning it is exposed to more sunlight and therefore more UV radiation, which would explain why its colors are often more vivid than anything else on the planet. Jupiter is not a one-storm planet either. A second oval storm, unofficially nicknamed Red Spot Jr., formed between 1998 and 2000 when 3 smaller storms merged into a single coherent system. It has since developed its own reddish coloration, possibly through the same UV-driven chemistry responsible for its larger neighbor. One of the most underappreciated aspects of Jupiter is its magnetosphere. The planet generates a magnetic field roughly 20,000 times stronger than Earth's, the most powerful planetary magnetic field in the solar system, surpassed only by the activity around the Sun's own sunspots. The source of this field is that deep layer of metallic hydrogen. As Jupiter rotates, and it rotates rapidly, completing a full day in just under 10 hours, despite its enormous size, the electrically conductive metallic hydrogen churns through it, generating a magnetic dynamo of staggering power. The consequences of this field extend far beyond Jupiter itself. The magnetosphere stretches outward in the direction away from the Sun for hundreds of millions of kilometers, forming a vast tail that, if visible, would span a significant fraction of the distance between Jupiter and Saturn. In the direction facing the Sun, the boundary of Jupiter's magnetic influence sits roughly 3 million kilometers from the planet. This has direct implications for the moons orbiting within that field. The 4 large Galilean moons, Io, Europa, Ganymede, and Callisto, all sit within Jupiter's magnetosphere. While this shields them from solar wind, it also means they are embedded within one of the most intense radiation environments in the solar system. Io, in particular, the innermost of the 4, moves through an especially harsh radiation belt that delivers lethal doses of radiation every single day. Any unshielded probe entering that region faces rapid instrument degradation. Any life as we understand it would not survive there. Jupiter's gravitational influence on the wider solar system is not passive. It is active, continuous, and in many ways foundational to the state of the solar system we inhabit today. The asteroid belt, which sits between Mars and Jupiter, is not a region where a planet failed to form. It is a region where Jupiter's gravity actively prevented one from forming in the first place. The gravitational perturbations from Jupiter kept the material in that zone too stirred up to ever coalesce into a stable world. The result is a scattered field of rocky and metallic debris rather than a 5th rocky planet. Jupiter also acts as a long-range deflector for objects moving through the outer solar system. Long-period comets, those arriving from the distant Oort cloud on trajectories that might otherwise intersect with the inner solar system, are frequently captured, accelerated onto escape trajectories, or destroyed entirely by Jupiter's gravity. In 1994, astronomers watched as comet Shoemaker Levy 9, broken apart by tidal forces on a previous pass, crashed into Jupiter in a series of impacts that left scars in the atmosphere larger than Earth. The energy released in each impact dwarfed any terrestrial natural disaster by many orders of magnitude. This protective role has been part of Jupiter's story for billions of years. And yet the relationship between Jupiter and the inner solar system is not simply benign. The same gravitational influence that deflects some comets also perturbs the orbits of others, occasionally sending objects inward rather than outward. Jupiter is simultaneously protector and, on rare occasions, threat. Humanity has sent a remarkable number of spacecraft to study Jupiter. The Pioneer missions in the 1970s gave us our first close photographs. Voyagers 1 and 2, passing through in 1979, revealed the ring system, captured stunning imagery of the Galilean moons, and confirmed the extraordinary volcanic activity on Io. The Galileo mission, which arrived in 1995 and operated until 2003, dropped an atmospheric probe directly into Jupiter's cloud layers and spent years in orbit mapping the moons in unprecedented detail. More recently, the Juno spacecraft has been orbiting Jupiter since 2016 and has fundamentally changed our understanding of the planet's interior. Juno's gravity measurements suggest that Jupiter's core may be far larger and more diffuse than previously thought, a fuzzy core that may extend outward to nearly half the planet's radius, potentially the remnant of a massive primordial planet that was absorbed early in Jupiter's formation. Upcoming missions promise even more. The Europa Clipper, launched in 2024, is on its way to make dozens of close flybys of Europa, searching for evidence of the subsurface ocean believed to sit beneath that moon's ice shell. The JUICE mission, launched by the European Space Agency, will eventually enter orbit around Ganymede, the first time any spacecraft has orbited a moon other than our own. Jupiter is not simply an interesting object at the edge of the asteroid belt. It is a fundamental part of why the inner solar system, and life on Earth, exists in the form it does. Its gravity sculpted the distribution of rocky material in the early solar system. Its magnetosphere continues to influence every moon in its vicinity. Its atmosphere preserves chemistry and physics we cannot easily replicate in any laboratory on Earth. We are still in the early chapters of understanding this world. Every mission has returned surprises. Every model has been revised. And with new spacecraft now en route to its moons, the Jupiter system is poised to become one of the most scientifically productive destinations in our solar system over the coming decades. Thank you for watching this far. Is there a specific aspect of Jupiter, its moons, its interior, its role in early solar system history, that you'd like to see covered in more depth? Let me know in the comments, and I'll see you next time.